Hello chemists, this is Ms. Placino and you are watching Screencast 14.2 on naming and drawing organic molecules. Today's lesson is a long one, so get comfortable, grab your reference table, something to write with, preferably a pencil, and get ready to work. This is arguably the most important lesson of the entire unit. You've got to be able to name organic molecules and you've got to be able to draw them. Before we get into naming and drawing, I just want to spend a little bit more time talking about where hydrocarbons come from. Hydrocarbons, as hopefully you remember from the previous lesson, or you could deduce from the name, these are molecules that consist only of carbon and hydrogen. A lot of our hydrocarbons are going to come from crude oil. And when you get crude oil out of the ground, it's a big mixture of all different sorts of hydrocarbons, some with really long chains, some with really short chains, and that mixture isn't particularly useful. But if we can separate the mixture out into its components, we're going to have tremendously useful molecules. The way we separate them is through something called fractional distillation. And you might remember the word distillation from much earlier this school year when we were talking about separation techniques. Distillation was a technique where we separated two liquids that would dissolve in one another based on boiling point. We can do the same thing with crude oil. Of course, we've got to be really careful. Crude oil is going to be flammable, as most hydrocarbons are flammable. So this is definitely not something you would want to try at home. Fractional distillation calls for a very large column. We're going to heat up the crude oil, and our lightest gases, the ones that, I should say the lightest molecules, the one with the lowest boiling point, many of which exist as gases at room temperature, are going to be able to float up all the way to the top of the column. So we've got really small carbon chains, everything from methane to butane. As we make our way down the column, we should get to heavier and heavier molecules. And you can see how different length carbon chains are used. Something like a alkane with 8 carbons in it is going to be octane. We use gasoline for cars. As you get to longer hydrocarbons, we can use them for oils, jet fuels, diesel fuels, even longer. And as we just kind of make our way all the way down the column, we get to things that are essentially solids, or just kind of like very thick viscous oils. And we can use them for fuel and for things like asphalt. So hydrocarbons, extremely useful. They show up in all sorts of places in your everyday life, even in places you wouldn't really expect. All right, so let's get into naming and drawing. In the previous lesson, we talked about the alkanes. Hopefully you remember that alkanes are saturated hydrocarbons, which means the bonds between the carbon atoms are all single bonds. We talked about a series of them. We looked at CH4, C2H2, C3H8, and it turns out that any hydrocarbon that has the general formula CnH2n plus 2 is going to be a saturated hydrocarbon, or an alkane. We took a look briefly at table P yesterday, or in the previous lesson, and you could see how the prefixes change. So if we have just one carbon, you get the prefix meth, 2 carbons eth, 3 carbons prop, and since all of these are saturated hydrocarbons or alkanes, they'll all end in ane. So you can really just split the name in half, really. And we all end in ane, which tells us that it's saturated, so single bonds between carbon atoms. And then the prefix is meth, means 1, eth 2, prop 3. So that's the number of carbon atoms present in the longest chain. All alkanes, regardless of how many carbon atoms are present in that long chain, will always end in ane. There are other types of hydrocarbons as well. We can see unsaturated hydrocarbons, such as the alkenes. Alkenes have at least one carbon-carbon double bond present. There are some examples: C2H4, C3H6, C4H8. You'll notice there is no hydrocarbon, or I should say alkene rather, with just one carbon. Hopefully that makes sense. We need to have a double bond present between carbon atoms, so there is no like methene. They take on the general formula CnH2n. And we would call the first one ethene. The second molecule is propene. The third molecule, butene. Again, we can split the name essentially in half. We see that all of them end with ene, meaning we've got at least one carbon-carbon double bond present. And actually in this case, because they're enes and not dienes or trienes, we have only one carbon-carbon double bond present. Again, we've got those prefixes, eth, prop, and now bute, telling us how many carbon atoms are present. As you would probably imagine, all the alkenes end in -ene. Our last family of hydrocarbons are the alkynes. Hopefully you can make the prediction that in an alkyne we'll see what type of bond between two carbon atoms. If you're thinking triple, you're absolutely right. Here are some examples: C2H2, C3H4, C4H6. General formula CnH2n-2. All of these general formulas, by the way, can be found in reference table R. Oh, I lied. Reference table Q, excuse me. See if you can take guesses on those three alkyne names. If you're thinking ethine, propyne, and butine, you're absolutely right. Oops, sorry guys. Same thing. You're probably getting sick of hearing me say this. We can split the names. Notice how the ending is all the same. That's telling us there is one triple bond between two carbon atoms present. And the prefixes eth, prop, and bute are telling us how many total carbon atoms are in the longest chain. All alkynes will end in -ine, Y-N-E. So what I want to focus on really is we'll start with alkanes. We'll go there first, and as the lesson progresses, we'll talk about how to name alkenes, alkynes, and a whole bunch of other organic molecules as well. All right, so here's an example of an alkane. How do we know it's an alkane? Well, if you look at the carbon atoms, there are only single bonds between carbons. It's a saturated hydrocarbon, and the only family of hydrocarbons, that are saturated are the alkanes. The first thing you do is count the number of carbon atoms in the longest chain. We're talking about a chain, we mean it's continuous, and you don't have to retrace any of your steps. So you should be able to connect them without having to trace over anything. So if I start at this carbon, I got 1, 2, 3, 4, 5, 6 carbons in my longest chain. I'm going to use table P to find the appropriate prefix. If I look at table P, the prefix for 6 is hex. And you'll probably find that as we're practicing this stuff that you start to accidentally memorize the prefixes. Still use your reference table if you'd like to, just to kind of double check. We know that alkanes, regardless of how many carbon atoms are present, are going to end in -ane. So really, we just have to take that ending, tack it on to the prefix, and the name of this molecule is hexane. In your workbook, there are a bunch of practice problems. In the interest of time and your sanity, I'm not going to go through all of them. There will be a link in the comment section of this video, or in the description section, I guess, that'll send you to the answer key so that you can check your work. But I really would encourage you to pause the video, try out the naming and drawing examples in your workbook, and then check your work to make sure that you've got the hang of it. This is, again, a really important lesson. Naming alkanes, alkenes, and alkynes can get kind of repetitive and boring, and quite honestly, those pure hydrocarbons make up a relatively small portion of all the organic molecules that exist. There are things called functional groups. And functional groups really are just an atom or group of atoms that are not necessarily part of the parent structure. When I say parent structure, I'm talking about that long, continuous carbon chain. Alkanes, alkenes, and alkynes, despite having different bonds between carbon atoms, are for the most part pretty similar as far as their reactivity is concerned. The second you start to add other elements, whether it's a halogen, nitrogen, oxygen, sulfur, phosphorus, whatever the case may be, you start to have a pretty big impact on the properties of a molecule. That's what's going to make a lot of our organic molecules just much more interesting to study, because they will react differently than just the simple hydrocarbons. There's a big relationship in organic chemistry between structure and properties. So here we have two different molecules. There are a number of similarities between them. Why don't you see if you can pick out the two differences? You might have noticed that in that hexagon at the bottom, you've got chlorine attached to the one on the left. You've got fluorine attached to the one on the right. Based on what you know about the different elements, what can you probably conclude is true about making this change? Well, it's not like it's that dramatic. Chlorine and fluorine are both in the same group of the periodic table. They're both halogens. They're going to have really similar properties. What's the other difference between the two molecules? The nitrogen up at the top, this one just has hydrogen attached to it. This has a CH3 group attached to it. Now, you don't know too much about organic chemistry just yet, but the hydrogen, and this is called a methyl group, this is a really important change. Both of these molecules are drugs, and in order for a drug to work, it has to fit into like a receptor in your body somewhere. And you can kind of think about it as like trying to fit puzzle pieces together. A really common change in organic chemistry is if an H is too small, to swap out for something like a methyl that's similar in polarity and even to a certain extent reactivity, but just a bigger puzzle piece. So based on the fact that these two molecules have strikingly similar structures and just very minor differences between the two, again, the change with the halogens and the methyl and the hydrogen, you should probably conclude that these are most likely very similar behaving molecules. We're going to see a lot of the same, or at the very least similar, chemical and physical properties. So it's actually really neat about organic chemistry. Just by looking at the structures of molecules, you can start to determine which molecules are going to behave most similarly. All right, take a look at Table R in your reference table. Table R goes over all the different functional groups that you are going to be held accountable for. You need to learn how to use this table and how to name and draw organic molecules. And that's really what we're going to be focusing on for the rest of the lesson. Okay, so with all the functional groups, we've taken our hydrocarbon. So when you go to name a molecule, what you want to do is take a look at the structure and see if there's anything present in that molecule, anything present in the structural formula that isn't just carbon and hydrogen. Hopefully in this case you see this bromine atom kind of jumping right out at you. This means that this molecule is not a simple hydrocarbon. Hydrocarbons are only carbon and hydrogen. We have a bromine present, making this a halide. Halides just mean that we have some halogen, either chlorine, fluorine, bromine, or iodine, present in your molecule. So instead of a hydrogen being there, we've got a bromine. So in order to name this molecule, what we want to do is name our longest continuous string of carbons, our parent structure. And then if you look at Table R, you've got different prefixes for chlorine, fluorine, bromine, and iodine. And then we have to tell people where that halogen is located. So let's kind of walk through this step by step. I want to count the number of carbon atoms in my longest chain. I've got 1, 2, 3, 4. So this is some type of, butane. I know the prefix but means 4. I've got all single bonds between carbon atoms. So that's going to be an alkane. Based on Table R, what prefix do I need to use with bromine present? Hopefully you're thinking bromo. And if you want to kind of make a space between the bromo and the butane, technically that's fine. It really should just be one word, but I'm pretty happy if you're naming things correctly. The last thing we need to do is explain where the bromine is. If you think about it, there are a number of places it can be. We've got it on this carbon, but it could very readily be replacing any of the other hydrogens. In order to express where the bromine is, we want to number our carbon atoms. So I can number from left to right, or I can number from right to left. I need to choose the numbering scheme that gives me the smallest or the lowest value for carbon. Yeah, so I'm going to cross out this top scheme. Numbering from right back to left gives me 2 versus numbering left to right, I get carbon 3. So I'm going to use or say this is 2-bromobutane. It doesn't matter whether that bromine's on the top or the bottom. In reality, this molecule is moving around, bonds are stretching and bending and rotating, so it doesn't matter. We just need to state what carbon it's on. So the correct name of this compound is 2-bromobutane. Again, you've got practice problems, try them out and check your work. Moving right along, we have alcohols next. We know this is not a simple hydrocarbon because we have this OH group present on the molecule. Technically, in organic chemistry, we call this a hydroxyl group. I know up to this point in time, we were calling it a hydroxide. Hydroxide is an ion. Hydroxyl is just an OH group that is bonded to the rest of the molecule. So it's a really small and subtle difference, but they're not technically the same thing. This is covalently bonded and not an ionic compound. When you are naming an alcohol, you are going to name the longest string of carbons, our parent structure. You're going to drop the E from the end of that name, add OL or all as a prefix. Then we're going to provide the locator in front of the name. So again, let's do this together. I've got 1, 2, 3, 4, 5 carbons all bonded together with single bonds. So I know the prefix for 5 is pent. It is all single bonds, so this is going to be pentane. I want to drop the E. Let's erase that. Maybe. Okay, does not want to let me. We'll add the suffix OL. So I'll turn that E into an OL. I need to provide a locator number. I can choose 1 or 5 as my locator number. I need to use 1. I always choose the lowest possible number. So the name of this molecule is 1-pentanol. The ethers are next. Ethers have an oxygen thrown in the middle of a carbon chain. So we've got 2 carbon chains separated by an oxygen atom. In order to name the ether, we're going to name each of these carbon chains. They're called alkyl chains. We're going to name the shorter of the 2 first and then end the name with ether. So before we get into naming the ether, let's talk a little bit more about what this alkyl chain thing is. Basically, you can think of an alkyl chain as being an alkane, at this point in time anyway, that is missing a hydrogen. So for example, if we've got a single carbon chain, if it's a molecule all by itself, it would be CH4. Instead of this oxygen being present, we'd have a hydrogen, and we'd call that methane. We don't have CH4, we have CH3. CH3 can't exist on its own, so instead of calling this methane, we're going to call this methyl. So in this case, I've got methyl and a methyl. So I can name this methyl ether. Or if you'd rather save yourself some writing, I can call this dimethyl ether. Either way is perfectly acceptable. I know that was bad, I just couldn't resist. We'll keep doing more practice with alkyl chains. Don't stress, really just name that carbon chain as an alkane, drop the E, and add the suffix YL. All right, we have aldehydes next. Aldehydes introduce this carbon double bond oxygen group, which is called a carbonyl group. And an aldehyde, the carbonyl group, and don't stress too much about the name, has to be terminal, meaning it must be at one of the ends of the molecule. When you go to name an aldehyde, name the parent structure, we're going to drop the E and add the suffix AL. So I've got propane in this case. All single bonds between carbon atoms has to end in ane. 1, 2, 3 carbon atoms, that's where the prefix prop comes from. I've got the C double bond O, so I need to get rid of my E and add the suffix AL. This is called propanal. I don't need to provide a locator because in an aldehyde, that C double bond O group is terminal. It will always be at the end. So technically it would be 1-propanal, and that's kind of redundant. So we end up just leaving it without a locator number. We have the ketones. Ketones are very similar to aldehydes, except now that carbonyl group, the C double bond O, is not at the end. It's somewhere in the middle of the molecule. Now we do have to use a locator. So we're going to name the longest carbon chain, our parent structure, drop the E off the end of the name of that alkane, and then add the suffix -one. So let's see, we've got 1, 2, 3, 4, 5, 6, 7 carbons. 7 carbons gives me a prefix of hept. It's an alkane, so that'd be heptane. It's a weird looking E, let's fix that. I'm going to drop the E, add the suffix -one, and I've got to state what carbon it's on. Looks like I'm going to want a number from right over to left. This is 3-heptanone. Please note, you can't have 1-heptanone. Why not? Well, if it's 1-heptanone, it's technically called heptanal. Remember, ketones have to have that carbon double bonded to an oxygen somewhere in the middle of the molecule. It cannot be at one of the ends, otherwise you're looking at an aldehyde. All right, we've got organic acids next. In organic acid, we have something called a carboxyl group. Our carboxyl group is the COO group. Carbon is double bonded to one oxygen, and then it's single bonded to an oxygen. And in the case of an organic acid, the hydrogen, there is a hydrogen atom that is bonded to the single bond oxygen. This is terminal. So again, it always has to be at the end. When we name an organic acid, we're going to name the parent structure, drop the E, and then change the suffix to oic acid. So I've got two carbons single bonded together. That would look like ethane. I know to drop the E, add oic acid. This is ethanoic acid, more commonly known as acetic acid. I'm not going to ask you to remember any of the common names. If you can name according to what you got on table R, I'm going to be really happy about that. Esters. Put a star next to esters. Esters tend to be some of the more challenging molecules for students to name. In an ester, that carboxyl group that we saw in organic acids is not at the end. It's not terminal. Now jammed somewhere in the middle of the molecule. And now instead of a hydrogen being attached to the oxygen with a single bond, we have an alkyl group. So these can be a little tricky to name. We want to name the alkyl chain first. Basically, side without carbon double bonded to the oxygen. We're going to drop the E from the root name of the carboxyl containing structure, so the side with the double bond oxygen, and add the suffix O8. So let's break this down. What you usually want to do, especially when you're first starting to name esters, is figure out which is the simple side, in other words, which side does not have the C double bond O, and which side is the fancy side, I like to call it, which side does have the C double bond O. I'll put a box around those two. You got that single bond oxygen separating the two. So this is the simple side first. This is an alkyl chain. We've got one carbon atom present, all single bonds. So the prefix is meth, and the suffix is YL. We have a methyl group. We're then going to name the other part of the chain. I've got two carbons single bonded to each other. Ethane. I'm going to lose the E and add the suffix O8. So the name of this molecule is methyl ethanoate. And again, this can be really challenging for students. A lot of people find it helpful right off the bat just to go through and box the two different parts of the molecule to really make it stand out. Once you practice, you'll definitely get better at that, but it can be tricky initially. Okay, that wraps it up for our oxygen-containing functional groups. Now we're going to move into a couple with nitrogen. The first one being the amines, or amines. Doesn't really matter to me how you say it. In an amine, we're going to have a nitrogen atom present. And at this level of chemistry, it's always going to be an NH2 group. Now, technically, we could take those hydrogen atoms, take them off, and replace them with alkyl chains, or those carbon-containing chains. I'm not going to worry about that at this point in time. If you take organic chemistry later, you can play that game then, not right now. This is a little bit different formula than what we've been looking at. This is more of the condensed molecular formula, or the condensed structural formula, instead of the regular structural formula. Amines are going to get named very similarly to alcohols. We are going to name the longest parent structure, drop the E off the end of that name, add the suffix amine, and use a locator. So I've got 3 carbon atoms bonded together with single bonds, propane, lose the E, add the suffix amine, and use a locator. So I've got 1 propanamine. 1 tells me where the nitrogen atom is. Prop tells me there are 3 carbon atoms bonded together. And the amine is telling me, well, it's this NH2 group. Good. And the last one that we've got on that table R, are the amides. Amides look a lot like carboxylic acids, or organic acids, I should say, except instead of carbon being double bonded to an oxygen and single bonded to an OH, now it's a double bond to an oxygen and a single bond to an NH2 group. So we have a terminal carbonyl That's C double bond O. And then carbon is also bonded to a nitrogen. Because it's terminal, are we going to need a locator number? No, definitely not. It always has to be at the end. When we name amides, we're going to name the longest chain of carbons, drop the E from the end of that name, add the suffix amide. So I've got 1, 2, 3, 4, 5. Prefix for 5, oops. Sorry, is pentane. I'm going to lose the E, add the suffix amide, or amide, and I don't need a locator because it is always at the end. Alright guys, that wraps up all of the functional groups that show up in Table R. Again, if you haven't been doing so already, you really should pause the video, try out the practice problems, check your answers against the key, and make sure that you're doing this correctly. It's really important. I would do that before we move on to any of the stuff later in this lesson, as it is more complicated. All right, I want to talk a little bit about naming molecules without functional groups. So instead of seeing things like halogens, oxygens, nitrogens, how do we name hydrocarbons that are not just simply straight chain alkanes? Just like we did before, we want to determine the prefix, basically, eth, meth, prop, but, so on and so forth, by counting the longest continuous carbon chain in the structure. Remember, you can check table P for prefixes. We're going to look for any unsaturation in the molecule, so things like double bonds or triple bonds. We need to indicate where the double bond or triple bond is. We're going to use those locator values like we did for things like the halides, again using the smallest possible numbers. We know that if we've got a double bond present, that is an alkene, and we need to end that with -ene. For example, name of this molecule is ethene. There's only 2 carbons bonded together, so we don't really need to provide a locator number there. And in a triple bond, if a triple bond is present between carbon atoms, that is an alkyne, and we need the suffix -ine. So this, C2H2, this is going to be ethyne. Again, we don't really have to say where the triple bond is because there's just the 2 carbon atoms. So that's what they're going to look like. Let's try this example. We're going to go through and determine the longest carbon chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. So a 9 carbon chain. What prefix do I need? I need the prefix non. Based on the type of bonds present between the carbon atoms, what suffix do I need? Well, you've got a double bond present between these 2 carbon atoms. That's going to make this an alkene, so we need to end in -ene. Finally, where is that double bond located? Well, hopefully by looking at the molecule, you can tell that we need to number from right to left. So I've got 1, 2, 3, 4. I'm going to stop it right there. Should I choose 3 nonene or 4 nonene? I want to take 3 nonene because I always use the smallest possible locator number. So put everything together. We've got 3 telling us where the double bond is, non telling us that we've got 9 carbons in our longest chain, and then the ene is again just reminding us that this is an alkene. Branched hydrocarbons. In my opinion, these are the toughest one for students to name. Our straight chain alkenes, alkanes, and alkynes are relatively straightforward. Once you get used to the prefixes and picking out what type of molecule is present based on the bonds between carbon, it's not too difficult. Naming molecules with functional groups, you've got table R to use, but naming our branched hydrocarbons, you're kind of on your own. So let's walk through this together. When we say a branched hydrocarbon, we're just talking about smaller carbon chains that are going to stick out from our longest continuous chain of carbon atoms. We call these alkyl groups, and this is the 3rd time this has come up in this lesson. Remember, alkyl groups are missing 1 hydrogen atom from the alkane with the same prefix. So we used this example before, CH4, hopefully you know that as methane. Here's my long carbon chain, and here's a CH3 group sticking off of it. I'm going to call this methyl. Again, you can think about that YL meaning missing a hydrogen. It's just going to be stuck onto another molecule because carbon always has to have 4 bonds. So let's look at an example. We want to count the number of carbon atoms in the longest continuous chain. So I can count 1, 2, 3, 4. I can count 1, 2, 3, 4. But there's no way to get to 5. I can't go 1, 2, 3, 4, 5. I have to retrace my steps, and that is not allowed. So with the longest continuous chain being 4, actually most people like to look at it this way, I'm going to use what prefix? Hopefully by now you're going to use the prefix but. This is all single bonded together, so we're going to use the suffix -ane for an alkane. That doesn't describe what the molecule looks like. This is definitely not just regular old butane. We've got this group sticking off of our butane chain. So you've circled our alkyl group. Oops. Let's name the alkyl group. Well, we got our 1 carbon chain, so that'd be methane, drop the E, and we'll call this methyl. I guess drop all of the ANE, we'll just use methyl. Up next, we have to say which carbon that alkyl group is on. Use the smallest possible locator number. So I could either use 1, 2, 3, 4, or 1, 2, 3, 4. Well, 2 is less than 3, so I'm going to use 2 as my locator number. I can put it all together. 2 methyl butane. So I'm going to look at it from backwards, back the name forward. Ane tells me all single bonds between carbon atoms. But is telling me 4 carbon atoms in my longest chain. Methyl is telling me that there is a CH3 group sticking off of this molecule. Well, where is it? Oh, it is off of the 2nd carbon. So again, these could be a little bit more work. Don't be fooled with the molecule kind of bending the way this one does. That's still a part of the longest continuous carbon chain. So these are going to take some practice. You've got a bunch of practice problems in your workbook. Take the time to go through them and check your work. Okay, so there are some really cool shapes that you can make with organic molecules. We talked about catenation in the previous lesson, and that's just the ability of carbon to bond to itself to form long chains, which we've been looking at, as well as rings. So these are called cyclical molecules or just simply rings. So we're going to count the number of carbon atoms in the ring and add the prefix cyclo to the parent structure name. So we've got these 3 rings. Well, I see 3, 4, and 5 carbons. So I know if it's 3 carbons, it would be prop. I've got all single bonds between carbon atoms, so this would be propane. And it is cyclical, or it is a ring. So I would just call this cyclopropane. Let's do another one. 4 carbons, prefix but. All single bonds between carbon atoms. Butane. It is a ring structure. It's closed off. Cyclo. What do you think the name is of that last molecule? Yeah, this is cyclopentane. And they're not drawn on here, but technically there should be hydrogen atoms every place else to make sure that carbon has 4 bonds. It's not uncommon to leave hydrogens off of structures. They're kind of implied that they're there. Sometimes on your ring structures, you have functional groups present. You only need to explain where the functional group is if there is more than one of them on the molecule. So let's take a look at our first problem. We've got cyclopentane. We just named that. That really doesn't account for all of the carbon atoms. We've got this technically CH3 group floating around up here, bonded to the top carbon. I would call this methyl. Methyl cyclopentane. Why don't I have to call this like with a locator number? Well, technically, no matter where you move that CH3 group, you can always just call it carbon 1. So as long as there's only one functional group or alkyl group sticking off of the ring structure, it does not need a prefix. Try the second one. This is definitely cyclohexane. Excuse me. I've got my 6 carbon atoms all bonded together in a ring, cyclohexane, single bonds. 1, 2, 3 methyl groups sticking off. So I would call this trimethyl. Oh, I'm making a mess. I need to state where these 3 methyl groups are. Let's call this 1, 3, 5 trimethyl cyclohexane. 1, 2, 3, 4, 5, 6. If you named it 2,4,6 trimethyl cyclohexane, you've got the right idea. But again, we want to use the smallest possible locator numbers. 135 is less than 2,4,6. And last but not least, this molecule, well, I got oct, cyclical, so cyclo-oct something. And I know those 2 O's together are a little bit weird, but they both go there. I've got a double bond present, so this is going to be cyclooctene. I don't need to say where the double bond is located. There's nothing else on this molecule as far as functional groups or alkyl groups are concerned. So cyclooctene does the job. All right, last but not least, we definitely can't talk about naming and drawing in organic molecules and not discuss benzene, C6H6. The structure comes up a lot in organic chemistry. If you Google images of organic molecules, you will very, very frequently see this ring structure. So we've got 6 carbon atoms bonded together in a ring with alternating double and single bonds. That's what we call an aromatic compound. Each of those carbon atoms has 1 hydrogen sticking off of it. So sometimes you'll see that represented with a hexagon and a circle in the middle. And sometimes you'll see it with a hexagon and then the double bonds drawn in there. There are things called pi electrons, and for the time being, you can just think about those as the 2 electrons that are present in the double bond. So technically, in a double bond, we've got 4 electrons being shared. We've got sigma bonds and pi bonds. We spoke about those during first semester. We didn't spend a ton of time on it, so I wouldn't be shocked if you don't remember it or it doesn't ring a bell. The big thing to know here is that these are delocalized. And all that really means is instead of, for example, this pair of electrons that I just circled being shared between carbon 1 and carbon 2, all of these pi electrons, so electrons in the double bonds, are shared between all of the carbons. That's why a lot of times you'll see benzene represented with a circle inside the hexagon. Those electrons in the double bonds don't belong to any carbon or carbons in particular. They are shared equally across all the carbons in benzene. Okay, I know I threw a ton of information at you and that was a very lengthy lesson. I am urging you to go through and work on the practice problems. You've got a ton of them that go along with the lesson, and then, my goodness, so many of them to keep on practicing well after the lesson. You have to be able to name and draw. If you can't name and draw, you are kind of dead in the water in this unit. So I don't want to scare you or stress you out, but this is important. And the good news is you've got your reference tables that you can really lean on for alkenes, alkanes, alkynes. You've got the prefixes there and all of your functional groups. Just the cyclical compounds, those ring structures, and branched hydrocarbons. Those are the only ones where you can't really use your reference table as a tool. All right, guys, I know that was a very lengthy lesson. Hopefully it was helpful, and thank you for tuning in.